And this one we can solve, and here are the 2 points. We have a formula for those 2 points. This is the 2 cycle, not the 4 cycle, the 2 cycle. Okay? And this only exists, you can see it's only real for a greater than 3. So what is happening? What is this? What's happening is that F2 undergoes a pitchfork bifurcation. F was a quadratic map. F2 is a 4th order map. And here's what it looks like. And before the bifurcation, for A low, it looked like this, and above, it looked like this. So it now has, an unstable fixed point surrounded by 2 stable fixed points. Those 2 stable fixed points are x1 and x2. This is F2 we're talking about, so that x1, if the limit cycle is x1, x2, x1, x2, we have x1 is a fixed point of F2, x1, x1, x2, and here we've got x2, x1, x2, x1, and the original one has become unstable, the original, okay? So that's just what's written here. We can go further and try and look at the stability of the 2 cycle, because that's what, you know, it's going to undergo a bifurcation too. So we can, we're thinking now of F2. We have a fixed point of F2. And so we're going to take its derivative, and we're going to see when it crosses -1 or 1. We use the chain rule. This is f prime of f times f prime, and that's the product of the derivatives of the two elements of the 2 cycle, which we got. We can do a lot of algebra, and we get this expression. Okay. When we finish plugging in for the expressions for x1 and x2, we get our expression a squared minus a squared plus 2a plus 4. And now, as before, what we want to do is check when it crosses 1. Or -1. Again, there are the 2 cases. Crosses 1, let's just take this -1, and we find here this is also going to be a quadratic function. And when it crosses 1, that's a equal 3. And again, that's the not surprising result. That was when it was formed. The a equal 3 we found before. That was this one here, 3. When you undergo a bifurcation, that is, you necessarily have a change of stability. So that's the not surprising one. Now, we look for when this product is equal to -1, meaning we're going to do minus a squared plus 2a plus 4 plus 1 and find its roots. So we do all that, and we get another quadratic, and we solve it. And here we find these 2 values, only one of which is positive, the other one's negative. And this is 3.44948. It looks like it's not 3.5. And you recall that was about when we found this 4 cycle. Let me see if we can get this back. We were at 3.5 and we had the 4 cycle, right? 3.5. Now, if you know, what's the joke about not 0 or 1, or anyway, 1, 2, many, or that's supposed to be some languages have only names for 1, 2, and then many. Anyway, once you've had a fixed point and a 2 cycle and a 4 cycle, you won't be surprised to find that there's 8 cycles, 16 cycles, and so on. The part that might be surprising is how they accumulate. We had to go from the creation of the cycle of the fixed point at 1 to 3 when we changed the a values. Remember, that's why I was kind of, I didn't want to go too far. You might have said, oh, you're not getting it yet, oh, just go further. But I knew what would happen if you go further. So the next one happens at 3.44948. The next one happens at 3.544. You know, they're very fine. At that point, if you want to find these things, you have to adjust it very slightly. So we can do that. Let's see, I want to be between 3.544 and 3.568. Well, I guess I'll be at 3.55. Okay, so stop. 3.55. Reset. Start. Hopefully this will be an 8 cycle. Stop. Clear. Start. Yeah, so this is an 8th cycle. You can see how it shadows the 4th cycle. You see how this is the splitting where there used to be 1 point here from the 4th cycle. This one is where there used to be 1 point here from the 4th cycle. And this one here where there used to be 1 point. And here you don't see it so clearly, but, well, you see it pretty clearly here, not so clearly there. Right, so this is the splitting of, this is the bifurcation from 4th cycle to an 8th cycle. And indeed, in numerical analysis, you know that you get this alternating stuff. If you take your time step too large, right, that's in numerical splitting, and that is this, that's that -1. That is exactly that. It's the -1 that happens, this one here, this -1. That's what numerical instability is, I think. When you say, in most cases, it does, I mean, I know the explicit Euler demonstrations don't, but are there other numerical instabilities that are not that? Do you know of in time integration? Doesn't it always do just that? So it's turning a continuous dynamical system to a discrete one, which then undergoes a period doubling bifurcation, which it shouldn't do if it were a continuous one, doesn't it? Okay, so we're almost finished with this part. I'm just going to say, kind of, yes, okay, so this is interesting and weird, and the very strange thing about this, besides being interesting by itself, it all accumulates. Okay, it goes to infinity at 3.569945, right? You know, really close to where we found that first period. And then there's more. We can take the difference in the delta values here, in the A values. Here we get 2 and 0.445. You can see they're going smaller. And we can take the ratios of these. Of course, these are getting smaller, but then what's not going to change is the ratio between this and this, this and this, this and this, this and this. You can see it's all about a factor of 4, and indeed it's converging to this value, 4.669. And this thing here, you might think it's a property of the logistic map, but it's in fact universal, meaning it's a property of anything with a quadratic maximum. And I think I may have mentioned this before, last time. I said that all, whenever you're looking for a root, basically they're all linear roots, no matter what they really are, because sufficiently close, it's linear. So too, when you have a maximum, it's always a quadratic maximum. Sufficiently close, it's a quadratic maximum. You do Taylor series and so on. Not quite. There could be an exception. It could be a quartic maximum, where the quadratic term is 0, and then it looks kind of like, like this to the eye, right? Or an 8th order maximum. But if you take your usual maximum, it's a quadratic maximum. You take the sine function. It's doing that. This is a quadratic maximum. If you look at the Taylor series, it has all the properties. So all functions with quadratic maxima do this. This is universal, basically, for all maxima. And what is strange about this, of course it's a strange result, it's interesting, but it was discovered in 1976. This is something that could have been found by Gauss, right, Euler, all those old guys. This is something really simple that you understand and that's universal. Now, you could say it was facilitated by the fact that calculators were invented, and to iterate a function, all you needed to do was push a key. But those old guys who didn't have calculators, they did a lot of hand calculation. They filled up pages and pages and pages. I don't know that would have stopped them. They could have calculated that, but they did not. And they did not know this. This period doubling stuff was invented in 1976, which is a mere 42 years ago, which is amazing because it's such a simple and general thing. It is absolutely astounding, and I can tell you more sociology of it. It's generally known as Feigenbaum's period doubling. For a long time it was known in France, as you might imagine, as Coulé-Tresser period doubling, right? And I happened, I'm older than I look, or so I like to think, or rather, I like to think I look younger than I am. So I was around when this was discovered. And I was around at a conference when Feigenbaum and Coulé-Tresser met. I mean, they probably met before, but when it was, and what I heard later about their conversation was kind of like this. Okay, I wrote this in my PhD thesis. They were all young people. I wrote this in my PhD thesis, but I that was before your article, because I just didn't think it was that worth publishing. It's just a chapter in my PhD thesis. So yeah, your article is first, but I did it first. Where Feigenbaum replied, he had submitted the article and had it rejected several times by someone who's still alive, a prominent guy, prominent editor of a journal, who had turned it down as trivial. It became the most important result, let's say, or one of the 5 most important results, say, in second half of 20th century mathematics, and it was turned down several times by different journals. So Feigenbaum said, I'm sorry, I know that's the date of my publication, but I actually did it before you, because the day I did it, the first day I first submitted, was a year or 2 or a couple months, say, before your thesis chapter. Oh, I see. And so Coulin Tresser stopped being quite so mad. They realized that Feigenbaum had really done it before them by, a year or something like that. And so there's all this nice sociology, that the idea that this important result that's so simple was turned down by an important specialist in combustion, right? The editor of Siam Journal of Applied Mathematics from 1970 to 85. So that'll who shall remain nameless, but now you can all look up who it was, and who still defends turning it down, and just its simplicity, and that there apparently, I mean, it's rare, but there still exist simple and universal things to be discovered.
Excuse me.
Yes.
Why did the editor reject it? Because now everyone really like it.
Well, I guess it looked too simple. I guess.
Simple.
I guess I mean, it looked too simple. Maybe it didn't realize the far-reaching consequence of it. It looked like perhaps a little game or something. I don't know. I don't know. I mean, that was what he said. I mean, surely he didn't think it was false. It was just not.
Surely Gauss knew this. This is sort of thing you perused it.
Yeah. Maybe he thought Gauss knew it. You just had to study your Gauss better or something. Okay. So then the more of the story. I mean. The easy part of the story stops here. Then there was this question of why is this universal, and then the normalization group. For what you do, okay, the normalization group is, everybody knows this word, very important, Nobel Prize to Wilson is his name, right, for it. And what is it? It's where you basically you take a problem and transform it to another problem, and simpler and simpler and simpler until it gets to which is what this kind of looks like. And what was realized was that, again, I'm not going to go through this, we're going to take a break very shortly, that the way to show this was to do a mapping on mappings. You would remember we've been doing f of x, but now take a t of f, take a mapping of mappings. And the way you do it is, here's this black mapping here. And now we're going to do this other mapping to it. We're going to multiply it by a constant. We're going to do, remember that the double map played an important role. Remember that the period doubling map of f was a pitchfork bifurcation of f. So you want your mapping, your t, to turn f into f of f. And then you want the t to turn f of f into f of f of f of f. And so on, and so they acted with this mapped t that basically was f squared, which meant taking this black map and then you turn it into the f squared, and then you rescale it and you get this, and then you flip it back and scale it and you get the red map. And so you see from this, just from what we did, that the map f, the black, is a fixed point of the operator t. You get the same map back again. After you do this stuff to the map, you get the same map. So you're going to operate, you do dynamical systems, but not on x's anymore, but on f's. And you're going to say, oh, there's a fixed point here. And the fixed point, and then they found the fixed point. You seek a fixed point, and you find a fixed point, and it's got it is a fixed point. There is a mapping. It's like the exponential cosine sine, it has a Taylor series which is infinite, and they calculated a bunch of the terms of it. And things are, and what all of this is based on is the stability or instability of that fixed point, meaning that map, as you're period doubling, you're basically iterating that mapping of mappings, and you go to a fixed point, and that fixed point is the same, it's, as you said, universal, and this and that. There, here's the limiting, here's the first few terms of that universal fixed point of that t that explains how the whole thing works. And I think that's where, oh, no, just a tiny bit, yes, this one here, okay. Who's seen this picture? Everybody, how many people have in their dormitory rooms? Okay, so what is this? This is the number A that we've been looking at. And remember, there's a single fixed point until we get to 3. And then we have a 2 cycle. There still exists, as in the bifurcation diagrams that we must have drawn at least once this time, no, apparently not. Okay, you remember from all the bifurcation diagrams from last time, we have these many pictures where we have this, right? So this original one still exists, it's just unstable, right? And so too, the original fixed point exists, it's just lost stability, and you go to the 2 cycle instead. And the 2 cycle exists, it's just that it's unstable, and you know how the 4 cycle. And so that's what, so you could, but just to make the diagram less messy, they're only showing the stable ones. So here there's the fixed point, and here's the 2 cycle, and here's the 4 cycle, and here's the 8 cycle. And then there's a 16 cycle, but again, you saw how fast they accumulate. The whole thing becomes infinite about here. But then there are these nice things after that, these periodic, there's a 3 cycle over here. You can see it, just, you see that line here and a line here? There is a 3 cycle, if A is high enough, I think if we can get the parameters sufficient there. And now what you perhaps don't quite see, maybe you see that it undergoes period doubling, and when a 3 cycle undergoes period doubling, it becomes a 6 cycle, and then a 12 cycle, and a 24 cycle, and so on. And that all accumulates here. And there's an infinite number of such things all through. There are 5 cycles, there's everything. There's anything you want to find, you can find in there. I guess let's see if we can find the 3 cycle. Okay, so apparently 3.83. We find 3 cycle. Let's see if we can do that. Um, 3.83. I'm not sure we can find, because you can see it requires a lot of digits. Oh, it looks, okay, so let's say do stop, let's do clear, let's do start. And here it is, 3 cycle. And if we went a little bit higher to 3.845, we would have a 6 cycle. Cycle. So there's all kinds of stuff there, and oh, okay. Let's do just a tiny bit more. Remember, we're talking about physics and why continuous systems, and why should. I mean, it's natural that you should feel kind of uncomfortable about discrete systems. When do they come up? What's the okay? And here is an example of one of the earliest. This was when it was all being discovered. The exciting thing is it was being discovered at the same time as it was being found in experiments. People were looking for it in experiments as it was being discovered. This is now, this is convection. Of course, you've seen convection. And this is a, excuse me, these are time series of, this is very high Reynolds number, Rayleigh number convection. And you see here the power spectra. You see that they correspond to these 4 Rayleigh numbers. And here you already, I believe you see, I think, you see a period doubling. Over there you see 2 maxima. And remember what we said, that what is period doubling in a continuous system? You had a limit cycle and you were going piercing, 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 and you go to a situation here, piercing, 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 piercing. So you have 2 different kinds of pierce. Here you'll have two maxima, or 2 two piercings of the Poincaré section, and that leads to a period doubling, because something that goes choo, 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 choo has a certain frequency, and something that goes choo, 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 choo has twice the period, or half the frequency. So that is, I think, this is the main one, and this is the one here, because it's got two maxima. And then it goes through, here are 4 different kinds of maxima. If you look carefully, it's hard to find this because I think I mentioned this 2 classes ago. This was all pre-web, pre-scanning. You know, the paper version looks okay, but you cannot find this very easily on the web because it's all scanned afterwards. It's not, you can't find it the way you can find modern stuff so easily, every diagram with full resolution, everything. So this was apparently the best I could do easily. So here appeared, this is a 4 cycle, this is a 2, 4, 8, and 16 cycles, and presumably you can see all those frequencies appearing. Again, the periods get twice as long, 4 times as long, 8 times as long, 16 times as long, meaning the frequencies get shorter, so you get all this. I think these are all this, yes. So this is the main frequency. This is when there's half of it here, and then there's half, and also quarters and eighths and everything. Oh, no, excuse me, this is the quarters. Right, there's a quarter, this is 8, and this is 16. And you can imagine it's hard to go further because you don't have that kind of control. It's even amazing to get there. You don't have that kind of 4-digit control over your control parameter. And, yeah, okay, so let's see this. Yeah, so this is about what we just said. That is to say, you start off with a limit cycle, and it could undergo a pitchfork bifurcation. That's start off with limit cycle, you form from it a Poincaré section, which is this piercing map, and if it undergoes a pitchfork bifurcation, which is the first thing that we looked at in the beginning of the class, well, that's when this limit cycle becomes these 3 limit cycles, one of which is unstable, 2 of which are stable. But there's another thing and that you could imagine looks like this in your time series. But when it does the -1 thing, what it does is it becomes a Mobius strip, and that's what we were looking at there. It becomes this limit cycle still exists, it's unstable, but there also exists a limit cycle which is twice as long, which goes around piercing in 2 different ways, this black point and that black point, making a kind of Mobius strip as it goes along. Okay, so we stop here, and the second half is about Cloquet theory. Okay, we stop and we take a break for 10, 15 minutes.